Hey guys, welcome back to O2I Institute, and I'm your instructor Brandon. We are gonna start with chapter 3 of the AP Calculus AB curriculum, and its continuity. For continuity is what is so let me try to define continuity here first. What I want to say about continuity is if it's like continuous is like if it's like without stopping. For example, a linear function like y equals to 2x, right? 2x plus 1. This is like a continuous function. And so will the quadratic functions like this. These are also continuous. All of them are continuous. So what is not continuous? So something that is not continuous is like something like this. So if I have a graph right here, and then there's a point like this, I have like a thing here, and I draw a circle, and then I draw a circle here like that. This is discontinuity because at this point it discontinues, so this point is not included. For example, let's call this x equals to -2, so it's discontinuous at x equals to -2. Okay, so next I want to talk about a continuity. Basically, what conditions have to be satisfied for a function to be continued. So continuous. So first, FC is defined. So this point, like if it's continuous at x equals c, this point has to be defined. Okay, it has to be defined. Also want to state that the other one is that limit of as x approaches c if fx exists. So what that means is like the both the left hand and the right hand limit are equal. So for example, something like this will not be equal because this is including. This is including. So this would not be equal to right hand and left hand. So this would also be discontinuous. So both the left hand and the right hand here has to be equals, like something like this, or something like this. Like except this is a limit, and then both the right hand and left hand are equal like that. So that's what the second condition is saying. And the final condition, which is this limit of x approaches c, fx is equals to fc. So it has to equal to the function value as well. So limit as x approaches c of f. Okay, let me write it. Let me just give you an example actually. So limit as x approaches 2 here of f2 has to equal to f2. Okay, fx here has to equal to f2. So you plug that in, so f2 is equal to f2. So this also has to be satisfied. So if any of these conditions fail, the function is said to be discontinuous at c. Okay, so I'll talk about discontinuity now, the opposite of the continuity. Okay, so there are 3 types of discontinuities, which is separately removable discontinuity, which is just a hole in the middle, like something like this. This is called a removable discontinuity. And then there's also a jump discontinuity, where the function jumps around like that. There's a jump, removable here. And then finally there's an infinite discontinuity, which is just an asymptote, basically, like this. It approaches like that, approaches. Okay, so it meets somewhere in like infinity. It meets infinity, or it just doesn't meet. Okay, so now I'm gonna talk about if so these are, this one is okay. This one is shown here, just the removable discontinuity. Just removable. This one shown here is, I would say it's also removable. And then here, yeah, this one's left hand limit and right hand limit is not equal. Discontinuous as well. Continuous. Okay, I do not know how to spell it, but it doesn't matter. So I actually want to talk about a simple thing called properties. Okay, so these are the specific properties. Just need to know these. Pretty simple. So if f and g are continuous at c, then the following are also continuous at c of k times f. Okay, take k times the function f, a constant times the function f, and f plus or minus g, and then f times g, or f divided by g. These are all continuous. Okay, all continuous. Okay, now I'm going to talk about the IVT, the intermediate value theorem. One of the three theorems tested, which is separately extreme value theorem, intermediate value theorem, and mean value theorem. So we're going to go straight ahead and talk about the intermediate value theorem. So if f is continuous on the closed interval AB, FA is not equal to FB, and K is a number between FA and FB, then there is at least one number C in closed interval AB such that FC equals to K. Okay, so this is basically the intermediate value theorem. Now we're just gonna go ahead and talk about some examples. So here, the first one is about continuity. So find the x values at which f is not continuous, which of the discontinuities are removable. Okay, so here we see that this one, here we can factorize it into x times x minus 1. So it's discontinuous at these 2 points, x equals 0 and x equals to 1. Okay, so here, if we plug limit as x approaches 0 in, we get it's negative 1. And if we plug limit as x approaches 1 in, we get it does not exist. So to remove this continuity here will be x equals 0 because it still has a value. Okay, so same with b here. B is the discontinuity that our x equals to negative 2 and x equals to 5. And then we know when x approaches negative 2, this equals to the limit function equals to negative 1/7. If x approaches 5, it does not exist. So the removal discontinuity will be x equals to negative 2. Same thing here. Discontinuity is at 8. It does not exist, so it does not even removal discontinuity. Finally, just an easy question here. A piecewise function is asking if it's is it like what value of a if s is continuous at every x. This is just an application of continuity. Because remember the definition of continuity, both the left hand and right hand limit has to be equal. So here, the left hand limit here is actually x squared minus 1 here, which equals to 8, and then the right hand limit here is 6a. So 6a has to be equal to 8, and a equals to 4 over 3. Why? Why does 6a have to be equal to 3? Because the left hand limit and right hand limit are always equal. So that's it for today's class, and see you next class.